All right, well, welcome to the last session, and our first speaker will be Simon Willerton, speaking to us about two traces.
Thank you. So first, apologies to people who've seen this talk before. As you know, I think by now, Steve and Bertfried sort of curated the meeting, I think, so suggested the talks that we should talk about, so I was quite happy to go along with that. But yeah, the downside is that some of you might have heard this before. Okay, so what I want to talk about is ways of having traces in two categories. And sort of the bottom line is that there's, certainly the way I'm doing it, there's two obvious ways to do that, and they give you sort of two nicely related answers in various situations. Okay, so let me start off by just asking a sort of a general question. Sort of an interesting sort of mathematical exercise. What is a trace? So that's an algebraist, I suppose, and a trace is something, some function which is sort of invariant under sort of commutation. The trace of fg is equal to the trace of gf. So if you think about the traces of matrices, this is the kind of thing you have. But that's sort of a slightly elevated point of view, because when you teach linear algebra to students for the first time, usually what you're interested in traces of matrices, and you're interested in it being invariant under conjugation with other matrices, so invariant under change of bases, basically. So a linear map, the trace is independent of the choice of matrix you choose to represent the linear map with. And you may observe that, of course, the second relation here is a consequence of the first. So if you've got something which obeys the first rule, then it's definitely going to obey the second rule, because you can just switch the A round to the other side and cancel them. But the two traces I'm going to come up with, one of them will satisfy one of these and one the other. But just getting back to this question, what is a trace? I mean, so thinking about matrices, I have a good idea of what the determinant of a matrix is. So it's telling me, well, my geometric way of thinking about it, it's telling me how much is altering the volume of things. If I apply a matrix to some figure sitting inside some n-dimensional space, then the volume will change in a way which is described by the determinant of the matrix. Whereas the trace, certainly is the way we introduce it in linear algebra, sort of sum up the entries of the diagonal entries of the matrix. It's not so obvious how to interpret that. I mean, I still don't really have an answer, but I guess these ideas I'll show you sort of came out of trying to think what a trace is, but I haven't got any closer to really a good answer to that. Anyway, so before getting on to two traces, let's have a look at sort of traces just in monoidal categories. So, as I say, your sort of standard notion of trace is the trace of a matrix, and so we want to generalise that to the trace of a linear map. So the categorical way of doing that is we think of the space of, the collection of vector spaces as being a monoidal category. So we want to be in this, so we're going to define traces in the settings of a monoidal category, and you should think of vector spaces with tensor product of vector spaces and the complex numbers as the unit for the tensor product. And just as in vector spaces, in a monoidal category we say an object V star is left dual to an object V if we have the following morphism. So this is supposed to be generalizing this idea of a vector space has well, the left dual of a vector space is going to be the linear maps to the complex numbers from that vector space. So in particular, we have, so in particular, if we've got the linear dual of a vector space, important point of convention here, so for historical reasons my morphisms tend to go from the right to the left, just to confuse you after that. So if we have an element in the dual and an element in the vector space, we should be able to evaluate the dual on the original vector space and just end up with a number. So we just represent this in this string diagram notation. So V star tensor V, and here I'm going to use the third dimension going upwards, so I'm thinking of this as sort of lying in a flat plane, which is why I'm drawing it in this way. I'm going to use the other direction in a minute. So V star tensored with V, and we've got a morphism which we draw as this green thing going to nothing, which is supposed to be the unit for my tensor product. So we have the evaluation map, and for vector spaces, the pairing between the dual and the original vector space is supposed to be non-degenerate, and we have to phrase that in a slightly convoluted way in the category theoretic language, but that's what we're generalising as the notion of non-degeneracy. So the way we state that is that we've got co-evaluation, which is a map from the unit object, the complex numbers in that case, to V tensor V star, such that the two so-called snake relations hold. So that if we do first we do the co-evaluation here, so going in that direction, and then we do the evaluation. So this is going from V star to V star tensor V star to V star, so that's just a map from V star to V star. That should just be the same as the identity on V star, and similarly the other way around, that should just be the identity map. So that's the notion of a left dual in a monoidal category. And if we say, well, we say that V and V star are bidual if also V is left dual to V star. So that means we have another two morphisms where the role of V and V star are switched around such that these are satisfied. So now, if we have a bidual for V and we have an endomorphism of our object V, then we can define the trace. So we just do a co-evaluation first. So we're going from the unit object, we come this way, we do the co-evaluation. So we've got V tensor V star, we apply F to V, so we've got V tensor V star, and then we apply the other evaluation here, and that gives us a morphism from the unit object to the unit object, and that's what we define the notion of trace in the monoidal category to be. So, although it doesn't look like it, if we work in vector spaces, then this gives us the usual notion of trace for an endomorphism. So just unpack that for a second. So that's supposed to be a linear map from the unit object to the unit object. So that's a linear map from the complex numbers to the complex numbers, which is just a complex number. So associated to a linear map, we get a complex number, and that's just the usual trace. I add up the diagonal entries of the associated matrix. So you can actually figure that out. It's not particularly obvious. Okay. And so, as we saw in Catherine's talk, we have this sort of cyclicity condition. So, normally, if we have a map between vector spaces, then we get the associated map going the other way between the duals. Now, that doesn't always happen in a nice way in an arbitrary monoidal category, so we want to impose this condition. So, if we've got a map F from W to V, and V and W have biduals W star and V star, then we get a map from V star to W star in one of two ways. We can either compose that way or we can compose that way. And we want them to give the same answer. So in most situations, in most nice monoidal categories, these things will work, but you just have to. It doesn't follow automatically. So in that case, we say that F is cyclic or has a transpose. And the reason it's called is cyclic is because the following cyclic property. So if we have two morphisms in our category, for W to V and from V to W, with one of them having a transpose, then this trace that I've defined, this round trace, satisfies this trace condition. So the idea is that F has a transpose, so we can move this F around here by using this condition. So what we need to do is draw this and get this right. so what we do is we just add in an evaluation and co-evaluation, so that's just the same as doing nothing, it's just doing the identity, so we can put that little kink in, but then we can use the thing on the, which one do we want to use? Yeah, the one on the left hand side, so that we can, if this is F, so this whole piece here, we can rewrite as F star there, and then we can get rid of that piece. So using the left-hand condition, we can move the F around, to this side, and then using this other condition, we can move it around the bottom to recover that. So if we have this cyclic condition satisfied for one of them, then the trace does satisfy this trace relation. Okay. So that's sort of the standard sort of picture for monoidal categories. I want to talk about monoidal two categories or monoidal bicategories. I'll use the words interchangeably. So, just give you some examples, the kind of examples I'm going to be thinking about. So, just give you a list of examples. So, not everyone is going to be familiar with all the examples, but hopefully at least one of them will sort of make some sort of sense to you. So, what do I mean by monoidal bicategory? So, I want to have a two category. So, I've got objects, morphisms, and two morphisms between the morphisms. And I've also got a monoidal structure, so I can multiply objects together, I can multiply morphisms together, and I can multiply two morphisms together. So I don't want to go into the details of exactly what kind of structure, what compatibility these things should have. I'll just give you the examples. So the heading on here. So here I've got my objects, my morphisms, what the composition is, and what the two morphisms are. So I've got the monoidal bicategory span, with the objects are just going to be sets, and the morphisms are going to be spans between sets. So a morphism from x to y is just going to be another set T with maps from down to x and a map down to y. So remember, our morphisms are coming in from that side, so that's a map morphism from x to y. And we compose using this pullback construction. I've got S and T, and I compose them by just pulling back just set-wise, so this is the set of points in T cross S, which have the sort of the same y point. And the two morphisms, so if we've got one morphisms, then the one T going from x to y and T prime going from x to y, then it's just a set map going from T to T prime, which commutes with the projection. So I should say...
Doesn't go from right to left.
Oh, thank you, yes. So I guess...
You've got the slide on upside down.
Yeah, right. Yeah, I guess it should be going upwards in fact. Yes, thank you. So I should point out that sitting inside here is in some sense, is the usual category of sets. Because if I've got a usual morphism, from x to y, and I don't know which way to draw it, that way or that way. So I've got f, which is a usual set map. Then I can take the span, which is as follows, which is just x goes to x. So inside of these sort of morphisms, you've got the usual morphisms from x to y, and you can check that when you compose two of these, then they compose as just ordinary sort of maps. So that's one example of a monoidal bicategory. I was sitting off the end there. I haven't told you what the monoidal product is. So you just take the usual product of sets. So that gives us a way to multiply objects together, just taking the Cartesian product of objects. And similarly, at the level of morphisms and two morphisms. Okay. So more algebraic example. BIM, the two category of bimodules. So the objects here are algebras over the complex numbers, let's say. So, or monoids in the category of vector spaces, if you prefer. And in this case, a morphism from A to B is not going to be an algebra map, but it's going to be a bimodule. So it's just a vector space on which A acts on the, I'm always getting left and right, mixed up, on the right, and B acts on the left. And again, well, I'll come back to that in a second. And we can pose them just by multiplying over the algebra in the middle. So we've got a bimodule, an AB bimodule on the right and BC bimodule on the left. We just tensor over B and get a vector space which A acts on the right and C acts on the left. So that's our composition. And then the two morphisms, if we've got a couple of bimodules, M and M prime, which are both AB bimodules, then we just look at the linear maps which commute with the actions of AB. So that's just the extra bit of structure between the one morphisms. And the tensor product here is just the tensor product over the complex numbers. So if we've got an algebra A and an algebra B, we can just tensor them together over the complex numbers to get an algebra A tensor B. And so we've got A tensor B, then we just get we need an algebra structure. So we just commute those two round. A tensor A, tensor B, tensor B. And then we just use the algebra structure in A and the algebra structure in B. So just using the usual tensor product over the complex numbers, we get a monoidal structure on this category. So the sort of the big daddy of those two examples is the sort of the enriched category picture for the sort of categorical hardcore version of this. So you take some symmetric monoidal category V, and you take the category, the bicategory of enriched profunctors or enriched modules over this. You either know what this is or you don't. So the objects are the enriched categories over V, and profunctors or bimodules are the morphisms as a composition, and the natural transformation between profunctors is the two morphisms. So let me just make the comment that bimodules, the objects here, the algebras over the complex numbers, so these are one object linear categories. So this is sort of a sub-example of this where V is the category vector spaces, and this is a sub-example of this where we just take category of sets. So don't worry about that example if you're not used to enriched category. But it does give you lots more examples, like you can play with things like metric spaces fall into this category of examples as well, this collection of examples, I should say. So now a more topological example this time, one that I'm interested in. So this is category of the monoidal bicategory of two tangles. So in this case the objects are going to be points in a plane. So this is going to be this purple plane, which is going to be sitting like that. And so if I've got a set of points in the plane and another set of points in the plane, what's a morphism between them? Well, it's going to be a tangle. So it's just a collection of strings in three-dimensional space which go from one set of strings to the other set of strings. One set of points to the other set of points. And you can pose just by gluing them together. So from 1 point to 3 points, we've got a little tangle there, and then we can just glue this one on to get our composition. And then the two morphisms, so we need morphisms between these morphisms, and these are going to be coborisms between these tangles. So these are tangles sitting in three-dimensional space, so we're going to have to take coborisms in four-dimensional space, so they're going to be surfaces whose boundaries are tangled. So obviously I can't draw very well in 4 dimensions, but let me make an attempt here. So just try and have a look at some examples here. So I've squished the old vertical dimension into nothing. So here I've got, say, a tangle at the bottom here, going from 2 points to 4 points. I've squished the vertical dimension down, but the idea is this is supposed to represent a surface in 4 space, going from that tangle at the bottom to this simplest angle at the top, so we've got some surface in between them. So these are just examples. Okay. So that's a much more topological example. I've lost my other slide.
What were those tori?
Oh, so the tori are quite happy just to sit there on their own. So they have no bound. So the idea is that the boundary of this surface should be the tangle at the bottom together with the tangle at the top. So you can just add in surfaces without boundary quite happily. So that is a cobordism whose boundary is the two tangles that we're interested in. So a cobordism from the empty tangle to the empty tangle is any closed surface. So the surfaces don't have to be connected.
And presumably, like the original morphisms can have closed loops that don't join up to anything.
Yes, very good. Yeah, so I didn't. Yeah, so we can have sort of tangles. Can be things like this, where we have sort of extra components here which don't have any boundary on them. Yeah. So we can also have those. Yeah. Oh, right. Thank you. Yeah, so that's quite a good tangle from 2 points to 2 points. I can have extra sort of link components which don't have any endpoints at all. Because you're going to get those when you glue together two sort of penny things anyway, so you have to include those. Right, and then just so the tensor product here is just disjoint union. So if I have a collection of 3 points and then a set of 2 points, I just stick them in front here. So I could stick, if I have a tangle like this and another tangle like that, I can just adjoin them in this direction. So that will be what my extra tensor structure is, my monoidal structure. And so two slightly more advanced examples. So this one comes up in sort of string theory or algebraic geometry. So the objects here are complex manifolds, not non-singular projective varieties, if you will, and the morphisms from x to y are going to be complexes of coherent sheaves over x cross y. And there's a way to convolve, if you have a sheaf over x cross y and a complex of sheaves over y cross z, you can convolve them to get a sheaf over x cross z, and the morphisms between two sheaves over x cross y are going to be the x groups. And similarly, there's a sort of a similar version for algebras, which is sort of generalising this picture. So rather than just having algebras, we have differential graded algebras, not modules, but complexes of modules, and some derived versions of that. So you can get, don't want to go into any details here, but you can get quite rich structures in here. So things that Catherine was talking about, like topological quantum field theories, can be viewed as sort of morphisms between various things in this picture. So if you're looking at functors from tangles to so in some versions of sort of constructing the Jones polynomial, some very highbrow ways of doing it, you look at ways of associating differential graded algebras to points, and complexes of modules to tangles, and so on. So there's sort of lots of structures between these which are also of interest, but I won't go into them today. So that's just a sort of family of examples, the kind of things that I'm interested in. Okay, so we had the notion of biduals for categories, monoidal categories. So we just need to tweak this a little bit to get the right notion for monoidal bicategories. So we've got a monoidal bicategory, and so an object now, V star, is going to be left dual to an object V if we've got the same sort of thing. So we want to have an evaluation map, so between the tensor of these two objects, just the unit object, and the co-evaluation going the other way. Now for categories, we said that this one morphism was equal to this one morphism. Now one of the sort of the fundamental rules about working with higher categories, or certainly with two categories, let's say, is that you generally don't say that morphisms are equal. It's like in categories, you don't tend to say that objects are equal, but they will be isomorphic. So we don't want these one morphisms to be necessarily equal, but we want there to be a two isomorphism between them. And we're going to have to actually specify what that isomorphism is. So we've got an isomorphism going that way, and an isomorphism going the other way. And similarly, we have an isomorphism between those two. And we have to have some coherence between these two isomorphisms here. Some extra data which just says that certain two morphisms are equal, the so-called swallowtail. So if we start like this, we add in, which one do we add in? We add in this one here, then we sort of switch these two critical points round, and then we use the other relation to get rid of that. So then we've got a two morphism from that to itself. That should be equal as a two morphism to the identity two morphism. So we can say equality here because we're looking at two morphisms. So that's just extra bit of data. So let me just mention here. So if I was sort of really getting into my string diagrams today. So what I would draw was this morphism, this two morphism I would draw as a surface. So what I want is something going from that sort of morphism to that morphism. And so I would represent it, as Catherine sort of alluded to, as a sort of a fold. So this is supposed to be the surface. Looking like that. So this is now supposed to represent, the surface is supposed to represent a two morphism between these one morphisms, and you can interpret the swallowtail relation as sort of cancelling out a certain fold, which I can leave you to think about if you these things. And so we also say that, as in the categorical, the one category case, if V also has a left dual, if V is also left dual to B star, and we say that the bidual. So the other thing we did with one category is we talk about transposes. So again, there's the situation where we have a morphism from W to V, a one morphism. So before we said it has a transpose if these two things are equal. If we make it as a map from V star to W star in these two different ways, using these two different, either use evaluation and co-evaluation, or co-evaluation and evaluation, then we should get the same answer. But again, we're in a two category, so we don't really want to talk about one morphism being equal. We want to talk about them being isomorphic. So we want to specify natural isomorphisms between these two things, in some sense. So we say if it's got a transpose, if there is a morphism from V star to W star, which is isomorphic to these two other ones. And there's some coherency, which I won't go into. But this gives us, for example, in the same way as we had before, that we can swap, if we've got an evaluation and we've got a morphism F, we can move it around either side and change it to an F star by using this little trick of just introducing a little curve and using other relation. Any questions so far? Okay, so let's just have a look at some examples. Get back to my examples. So for span, so the objects were just sets, and it turns out that the dual to a set X, so I should say, rather unsurprisingly, all the examples I gave before are going to turn out that each object has a bidual, and all the morphisms have transposes. So in the case of sets, if we just have a set, then its bidual is just X. So we need evaluation and co-evaluation maps, so let me just say what the evaluation map is. So we want a morphism from X cross X to the unit object. So the product is just Cartesian product, so the unit object is just a one-element set, which I'll call star. And so we want to span from X cross X to star, and it turns out that you can just take X as the set, take a diagonal map from X to X cross X, and just the terminal map from X to the 1 point thing. So that, and the co-evaluation is supposed to be a map from star to X cross X, and that's the obvious thing reversed around. And so we also want morphisms to have transposes. So remember, a morphism is just a span here, and the transpose of a morphism is supposed to go from the dual of Y to the dual of X. So, but the dual of Y is just Y, the dual of X is just X. So the transpose should go from Y to X, but it's just reorder your span. Okay, so just switch around the legs. You've still got maps, you just change your mind as to which is which. Okay. So with bimodules then, the objects are just algebras, so the bidual, so the dual to that in this sense is the opposite algebra. So it's just the same vector space, but you just reverse the multiplication. So x times y is now defined to be what used to be y times x. And we want evaluation, so that should be a bimodule from A tensor A op to the unit algebra. The unit algebra is just the complex numbers, so we just want A tensor A op bimodule, sorry, something which is bimodule for A tensor A op on the right and C on the left. But we can just take A. So having something which A op acts on the right is the same as having something on which A acts on the left. So that's the usual way to switch between left and right modules for algebra. So we can just take A itself, and it just acts on itself on the right by multiplication and on the left by multiplication, but we can think of that as acting on itself on the right by A tensor A op. Okay. And the co-evaluation is a similar thing. And now, what's the transpose of a morphism? So a morphism is just a bimodule from A to B. So we want something from B op. So it should be, we switch around, it should be from the dual of B to the dual of A. So it's just something from B op to A op. But as I've just said, a right B op module is the same as a left B module. So we just think of M, which is A acts on the left, but that's the same as A op acting on the right. God, I've got my left and right wrong way around. Yeah, A acting on the right is the same. So we just take the same thing, but just think of it in a slightly different way. And this generalises again to the enriched category setting. Again, go too much into details, but the dual of an enriched category C is the opposite category. The evaluation is just the Hom functor from C op tensor C tensor the unit thing into your enriching. If you've got a morphism, which is just a profunctor, C op tensor D, you just think of that as a functor from D op tensor C op to B. So you just get another way. And if you just specialise, get the previous two cases. And two tangles now. So again, we have self-duality. So if we have an object which is just a collection of points in the plane, then its dual is just another collection of points in the it's the same collection of points in the plane. And evaluation now, so it should be a morphism from that set of points, tensored that set of points, to the unit thing, which is no points. Remember, tensor just means stick these points next to each other, and so the evaluation map should just be a tangle from this set of points doubled to nothing, so you just create a horseshoe. You just join up each of the points. And the co-evaluation will be the way the other thing round, and then hopefully you can see that you're automatically going to get the so we have sort of the evaluation, and we compose it with the co-evaluation in that way, then that's going to be isomorphic to just the identity on the 2 points. So the co-evaluation and the evaluation maps will satisfy the snake collection. So it's not so obvious in these cases. I mean, it's an easy calculation. Anyway, and so if we have a morphism, which I'm just representing schematically here, so that's supposed to be a tangle in this brown blob here. We want something, a transpose, so going in the other direction between the duals, but the duals are just the same thing, but we just rotate it round, and that would be the transpose. So that's like if we just stuck, remember that's like sticking an evaluation on that end and the co-evaluation on that end, and then sort of pulling the strings tight, that will just rotate the tangle around. So, and similarly, the last 2 examples are just very similar to the top examples. So the derived, so the sort of the derived version of this, you get a very similar picture. A complex manifold is self-dual, and you get a evaluation sheaf, which is just the structure sheaf of the diagonal, so it's a bumped up version of this. And similarly for derived categories of modules, pretty much just the same as this simple picture, but just put the word derived everywhere. So, okay, but certainly don't worry about those 2 last examples. Okay, so not got to the notion of what the trace is. Hopefully you should know what I'm going to do next. So I've got this idea of objects and biduals and evaluation and co-evaluation in a monoidal bicategory. So it's now straightforward to define this sort of round trace. So if we have, so we're working in a monoidal bicategory. If we have an object with a bidual and we have an endomorphism from V to itself, we just define the round trace in this way. So we just do exactly the same thing because we've got essentially the same structure, and we just do the co-evaluation, apply F to the V side, and then do the evaluation, and we get a one homomorphism from the unit object to the unit object. And there's something called a round trace. So it's round. Okay, and this this deserves the name trace for exactly the same reason that we had for just the ordinary category case. We don't get the traces of F and F composed with G and G composed with F being equal, because remember they're one morphisms, and in a 2 category we're never going to talk about one morphism being equal really, we'll just say they're isomorphic, so there's going to be a canonical 2 morphism which could be an isomorphism. So if we have F from W to V and V to W given by G, with one of them having a transpose, then we can do exactly the same trick. So with the round trace is just defined in this way, we've got a 2 isomorphism that brings F round to make it at the expense of making it a dual going from W star to V star, and then again we can bring it round this side and we get these isomorphic. So that's just very much mimicking the situation in a monoidal category, but we're just taking account of the fact that we've got this extra levels of structure. The 2 morphisms. Now it turns out that isn't the only way to define a trace. So that's sort of the obvious one if you've been thinking about monoidal categories, but so the following one sort of crops up in many situations. So important thing here is that if you just have a bicategory without a monoidal structure, so we've just got 1 morphism and 2 morphisms, we haven't got this tensor product, then we can also define this other thing which deserves the name trace. So suppose we have an object of a bicategory, and again we've got a morphism from V to V. We define its diagonal trace, this time to be the set of two morphisms from the identity morphism on V to F. And I'm just going to draw this sort of schematically. So this is the set of, this is morphisms going vertically, so this is two morphisms going from the identity on V here to morphism F from V to V. So this I call the diagonal trace, because this is more akin in certain situations to picking out the diagonal entries out of a matrix, but I won't go into that. But that's where the name comes from. You can justify that in that way. So this is quite a different nature to the other one. So here we're taking a set of two morphisms. The other one, what we did was we start with a morphism, and its trace is itself a one morphism, but from the unit object to the unit object. This trace is not a one morphism, but it's a set. It's just a set of two morphisms from the identity to F. So it looks quite different, but why do we call it a trace? Well, we call it a trace. It's got a trace property. So suppose we have two maps, V to W and W to V. Then we want some relation between. Oh, hang on. Right, sorry, I was confusing myself because I was expecting the other trace property. But we don't get the same trace property, we get this other one. So if we have a morphism, so the idea is we're looking at the trace of F. So F is just something going from V to V, but we've got two maps from V to W and W to V, and we've got some extra bit of data. We've got a two morphism going from the identity on W to doing A prime first and then A. So that's just a map from W to W. So which I draw at the bottom here. This is this thing that's going from the identity on W to A prime. So we get a two morphism from this trace. So sorry. No, we don't get a two morphism. These are sets. What we get is a set map from the set here to the set there, which is just composed with this two morphism. So and in sort of in particular, let's trace property properly. So if we have an equivalence between objects V and W, then this is just going to be the A prime composed with A is going to be, so these are equivalences, then A prime composed with A is going to be isomorphic to the identity. So these sets are actually equal. So the trace, diagonal trace of F is equal to this sort of conjugated, the trace of the conjugated version of F. So this is a different trace property, but it certainly deserves the name trace. So these are two kind of quite different things. So what we had was, if we had the monoidal two category, we have this, and we have one morphism, say, coming this way, then we use this the monoidal plane. So we don't worry about the two morphisms, but we sort of draw circles down here, and we get a notion of trace. But we could have just used the two category structure, ignore the monoidal structure, and we get a trace by thinking in this direction. So we get these sort of two orthogonal notions of trace for a one morphism. So one trace is one of the traces will give you a morphism, and the other one will give you a set. So they look kind of different. Okay, so let's have a look at our examples again. So if we take bicategory spans, so an endomorphism, so we're going to take the trace of an endomorphism. So an endomorphism is just a span from X to X, and the trace, well, the round trace, if you do the calculation, it's the loops in T. So the loops in T, I mean, this is supposed to be, the round trace is going to be a morphism from a span from the one object set to the one object set. But that is just exactly the same as the set. So we've got a span T, star, star. But that's no extra data. So a morphism from star to star in this category is just a set. So the round trace should just be a set, and the set is just a set of points which go, if you go by that projection or that projection, you end up at the same point in X. So I just call these loops. They've got the first, I think of that as sort of an endpoint, the two endpoints of T. So it's the set of points in T which project to the same point. But the diagonal trace is going to be the set, another set, and it's a choice of loop for each X in X. So at each X in X, it's just going to be a element in T which maps down to X through both of these. So we get two sets which are slightly different, but they're both sets in this case. I should add, right at the beginning I said that if we have a map from X to Y, then we get a span. But if T is just coming from this thing here, this example here, then I guess the round trace of this span here is, well, if you check what a loop is, it's just the things which, so that should be an X there. It's the things where the identity is equal to F. So this is the set of fixed points of F, which is another sort of a good test for a trace. So the trace of a morphism, a map between sets, is just going to be the set of fixed points. So that's a nice trace-like notion. Anyway, so we've got two things which are sets. So now, for bimodules, an endomorphism is just an AA bimodule. If you work out the round trace, so this should be a one morphism from the complex numbers to the complex numbers. So this is a module over the complex numbers, so in other words, just a vector space. And it turns out that it's just the module M divided by the left action by A minus the right action. So this is a classical thing, the set of co-invariants of M. And if you do the diagonal trace, so this should be a set, but it turns out to have this, it's the set of invariants. It's the points in M which have the same action on the left and the right by M. So it sort of seems to be some interesting duality between these, even though these two traces a priori are completely unrelated. So, I go on here. So looking at this sort of, I just realised that this is this can be simplified rather. So if we're in the sort of the enriched picture, then the round trace can just be written as this. Oh, is that an end or a co-end? That's a co-end, thank you. Right, so it can just be written as a co-end, and the diagonal trace, it turns out, just you do the calculation and it just comes out to be this end. So there's a sort of automatically this interesting duality between these two things. In fact, well, yeah. So a priori, as I say, these completely defined in completely unanalogous ways, and you just end up with some things which look pretty naturally dual. In fact, yeah. So this is something of a mystery why that's true. Okay, in the case of two tangles, you get something rather different, where the round trace and diagonal trace are quite different. So endomorphism is just a tangle from n strings to n strings, and the round trace, you just connect it up, you just get a closed link. So you just get a link where you just close up all the ends of the tangle. So that's a link. And the diagonal trace, so this is supposed to be the set of all cobordisms from the trivial tangle on n strings. So that's just the identity, is we just join up all these strings straight to the tangle that we had, to whatever tangle we wanted. So we take all these cobordisms in R4, it's the set of them. So these are kind of unrelated in any obvious sense. They don't have the nice duality that we get in that n-range picture. Okay, and just to show you what happens in this sort of derived case, so we have, you can work it out, turns out that if we have some sheaf over x cross x, you get something called the Hochschild homology of the sheaf, and the diagonal trace gives you the Hochschild cohomology. And similarly, if we have a module over some differential graded algebra. In one case we get the Hochschild homology, and the other turns out we get the Hochschild cohomology. So this strange duality sort of pops in, pops out straight away. Okay. So just finish with 2 slides. Okay, so in vector spaces, the dimension you can define the dimension of a vector space to be the trace of the identity, which is the sum of entries of the diagonal of the identity. And just take that to be the definition of the dimension. So analogously, we can talk about the dimension of an object in a monoidal bicategory. We just take the dimension. We've got 2 of them. We just look at the identity morphism on V, so we can take its round trace or its diagonal trace. So the round dimension again is going to be morphism from the unit object to the unit object, and the diagonal dimension is going to be the set of 2 morphisms from the identity to the identity. And so two kind of interesting things here. So automatically, this 2 morphisms from the identity to the identity, we can compose them. So this is a commutative monoid by the usual argument. Just got a morphism from the identity to the identity and another one. We can just compose them. And the diagonal trace acts on the diagonal dimension, which is this commutative monoid, acts on the round dimension. So what that means is we have a set here. We get a map to the set of 2 morphisms from this one morphism to this one morphism. So there's sort of extra structure associated to every object we've got. So we can just look at what this gives us for examples. So I'll just finish with this. So for every object in our categories, what we want, we get a commutative monoid, and we get something on which that commutative monoid acts in an appropriate sense. So unfortunately for the set, we don't get a very interesting commutative monoid. We just get the 1 element monoid, and the round dimension of a set is just the set itself. Slightly more interesting for an algebra. So there, the commutative thing associated to it is just the centre of the algebra, and this sort of abelianization is the round dimension. And again, we've got this sort of co-end and n formula for the case of a V category in general. And for the tangles, if we just have n points, then the round dimension is just the n component, unlinked, just n circles. But the diagonal dimension is this set of cobordisms from the trivial tangle to itself. So it can compose cobordisms by sticking them on top of each other. That gives us our algebra, our monoid structure there. Obvious immediately that that's commutative. And then finally, these sort of 2 derived versions associated to a complex manifold. We have its Hochschild cohomology. Cohomology, as usual, is an algebra. And we have the cat product by which it acts on the homology. So you would cover the sort of standard homological structures between homology and cohomology in this way. And similarly, the dimension of a differential graded algebra, again, is Hochschild homology and cohomology. Okay, so I just wanted to give you this sort of idea of how with the monoidal 2 categories, we have these 2 ideas of trace in these 2 orthogonal directions, if you like, and in many examples they give you sort of interestingly related answers.
Do we have any questions or comments for Simon?
So your round trace, it gives you a scalar, and the way you define the diagonal trace, it gives you a set.
Yeah.
Is there some intuition, or is there always a way that you get some sort of structure of the co-thing of your scalars on that set?
No. I mean, so that's no. That's sort of a bit of a mystery. Okay. Yeah. I mean, if you have any ideas, I'd be interested.
All right. Well, since we're running late, I think we'll save any other questions for afterwards for the pub session. And let's thank Simon again.